All right, let's dive into one of the biggest feuds in all of physics. Think of it as a cosmic title fight for the soul of the universe, pitting an invisible, mysterious substance against a radical new theory of gravity.
So here's the deal. For almost a century now, astronomers have been staring at galaxies and realizing they're spinning so fast they should be flying apart at the seams. I mean, literally. The amount of stuff we can see, all the stars, the gas, the dust, it just doesn't have enough gravity to hold it all together. So what gives? Are we missing something, like 85% of all the matter in the universe? Or is our understanding of gravity itself just wrong?
And that single question has kicked off this incredible scientific showdown. In one corner, you've got the reigning champion, dark matter. This is the idea that there's a whole new kind of substance out there that we just can't see. And in the other corner, the scrappy underdog, the challenger, a theory called MOND, which says, forget new stuff, we need new physics.
All right, section 1. So how did we even get here? Let's back up a bit and see how we first realized something was deeply, fundamentally wrong with our picture of the cosmos.
It all started way back in 1933 with an astronomer named Fritz Zwicky. He was looking at the Coma Galaxy cluster, and when he did the math on how fast the galaxies were moving, he realized there had to be way more mass holding them together than what he could see. But the real bombshell, the thing that made everyone sit up and listen, dropped in the 1970s thanks to the incredible work of Vera Rubin. She measured how fast stars were spinning inside galaxies, and she found something completely bizarre. Stars way out on the edge were moving just as fast as stars near the center. According to everything we knew about gravity, they should have been moving much slower. It was undeniable proof that galaxies were behaving as if they were packed with invisible mass.
Okay, on to our next section. So faced with this puzzle, the vast majority of scientists came to one conclusion. There has to be a new, invisible kind of matter out there. So let's meet the reigning champion, dark matter.
The idea is pretty straightforward. This dark matter is made of some new kind of particle that doesn't give off light, doesn't reflect light, it doesn't interact with light at all. It's totally invisible. The theory goes that it forms these huge spherical halos around galaxies, kind of like a giant invisible cloud. And it's this cloud that provides all that extra gravity needed to keep the stars in check. And we're not talking about a little rounding error here. We're talking about 85% of all the matter in the entire universe.
And look, this idea isn't just some wild guess. It's the absolute cornerstone of what we call the standard model of cosmology, or lambda CDM. And for good reason. It works really well. It perfectly explains the patterns we see in the afterglow of the Big Bang. It predicts the enormous web-like structure of the universe that we see today. And it even explains how galaxies grow over billions of years by gobbling each other up.
But what if everyone's wrong? What if we've been chasing a ghost this whole time? A small but vocal group of rebels says the problem isn't missing matter. The problem is our understanding of gravity itself. So let's bring in the challenger, MOND.
The idea, cooked up by physicist Mordehai Milgrom back in '83, is pretty radical. It says, hey, maybe Newton's law of gravity isn't the whole story. He suggested that when gravity gets really weak, like it does in the far-flung outskirts of a galaxy, it behaves differently. It gets a little bit stronger than we expect, and it doesn't fade away so quickly.
And the whole theory boils down to this one single new number, a new fundamental constant of nature called A0. It's an incredibly tiny acceleration. Think of it like a threshold. In high acceleration places, like our solar system, everything works exactly like Newton said. But once you drop below this tiny threshold, out in the cosmic hinterlands, gravity's rules change.
You see, for Milgrom and his followers, dark matter is just, well, it's a fudge factor. They compare it to the ether, that invisible substance that 19th century scientists thought filled all of space so light waves could travel. It was a placeholder that everyone believed in, until Einstein came along and showed it wasn't necessary at all.
All right, gloves are off. Let's head into the galactic arena for round one. And this is where MOND really comes out swinging.
This is where MOND lands its biggest punch. It doesn't just explain things after the fact, it makes an incredibly bold and precise prediction. It says if you tell me where all the visible stuff in a galaxy is, the stars and the gas, I can tell you exactly how fast any part of that galaxy should be spinning. No wiggle room, no extra knobs to turn. And when we look at the data, boom. It's called the radial acceleration relation, and it's been checked in over 150 different galaxies, and the fit is just stunningly good. The actual observed acceleration lines up almost perfectly with what MOND predicts. Now here's the kicker for dark matter fans. In their model, there's absolutely no reason this relationship should be so clean and predictable.
This gets at the core of the debate, really. MOND is rigid. It makes a prediction, and you either prove it right or wrong. Dark matter, on the other hand, is super flexible. You can basically tweak the amount and shape of your invisible halo for every single galaxy to make the data fit. And critics say that feels a lot like adding epicycles to save a broken theory.
But don't count the champ out yet. For round 2, we're zooming out, way out, to the cosmic scale. And this is dark matter's home turf.
Okay, this is dark matter's knockout punch, or so they say. It's called the bullet cluster. What we're looking at here is the aftermath of a massive collision between two galaxy clusters. The galaxies themselves, being mostly empty space, kind of passed right through each other. But the hot gas that makes up most of the visible matter slammed together and got stuck in the middle. Here's the crazy part. When we map out where the gravity is, it's not in the middle with the gas. It's out on the sides with the galaxies. This is exactly what you'd expect if the galaxies were dragging invisible clumps of dark matter with them. And it's a huge, huge problem for MOND.
And it's not just the bullet cluster. MOND seems to have a bit of a cluster problem in general. While it gets rid of most of the missing mass problem in these giant structures, it doesn't quite get rid of all of it. There's still a little bit of gravity left to explain. Now, for MOND supporters, this could just be normal stuff we haven't found yet, like super dim stars or faint gas. But for critics, it's a big crack in the theory's foundation. All right, time for what might be the final round, or at least the most current one. The science here is still hot, and it's messy, and the battleground has shifted to something much closer to home: wide binary star systems. So these are pairs of stars that are orbiting each other at enormous distances. Their gravitational pull on each other is incredibly weak, so weak, in fact, that it falls right into that MOND regime. They're the perfect slow-motion laboratory to test this stuff. And in 2023, a study came out that was a massive win for MOND. They looked at thousands of these pairs and found a clear signal that their motions were deviating from Newtonian physics in a way that perfectly matched MOND's predictions.
Case closed, right? Well, not so fast. Just a year later, another team takes the exact same data, runs their own analysis, and comes to the exact opposite conclusion. They found the stars were behaving perfectly fine, just as Newton would expect, and that their results were in strong disagreement with MOND. And this just brilliantly shows you how tough this science is, where two different teams can look at the same universe and see completely different things.
So, where does that leave us? Who wins? Well, the truth is, there's been no knockout. The judges are still deliberating.
So let's look at the final tale of the tape. It really comes down to this massive trade-off. On the scale of individual galaxies, MOND has this spooky, incredible predictive power. But on the grandest cosmic scales, galaxy clusters, the entire universe, the Big Bang itself, dark matter fits the data beautifully.
And that leaves us with this incredible fundamental question. Is the answer a mysterious new particle that's just really, really good at hiding from us? Or does it demand that we rethink one of our most sacred laws of physics, one that's stood for over 300 years? For now, the search continues, and the clash for the soul of cosmology rages on.